Hello students, I welcome you all to my channel Engineers Academy. Do hit the subscribe button if you haven't done it yet. Now we are going to solve this problem which says that the member is supported by a pin at A and cable BC. So we have a pin support at A and this cable BC, and it is said that determine the components of reaction at these supports if the cylinder has a mass of 40 kg. So this cylinder has a mass of 40 kg, so we have to find the tension in this BC rope which is providing the support, and that tension will be acting in this direction. And here we have this pin support. So as we can see that this pin can provide the resistance, the reaction in the X, Y and Z, that is the force reactions. So if I show those reactions at A, so we will have AX reaction. Let's say that it is going to act in the positive X. Let's say this is AX, and then it can provide the AY support reaction, since this pin does not allow the member to move in the Y direction. And similarly, it can also provide the support reaction force in the Z direction. This is AZ. And now as we can see that this pin can also resist the rotation about the x-axis. So it can provide the resistance along the x-axis, that is the moment along the x-axis. So let's say that, let's assume that we have this red one is, let's say, MAX. This is MAX, the moment provided along the x-axis, the moment support that it provides about the x-axis. And similarly, this can also provide the moment support about the z-axis, since this pin or this member cannot be rotated. So this pin is providing the reaction in the moment reaction about the z-axis. So let's say that we have the MAZ in this direction. So this is AZ component, and this red one is MAZ. So let me write that this is MAZ. And similarly, as we can see that this pin support cannot provide the moment reaction about the y-axis, since it is free to rotate about the y-axis. So we don't have MAY. So the MAY component, the MAY, the moment about the y-axis reaction is 0. So that is why we are not considering that. So we have AX, AY, AZ, and we have MAX. This is assumed to be the counterclockwise moment. If we curl our right hand fingers in this direction, so our thumb will point out in the positive X. So this means that this MAX is assumed to be counterclockwise. And similarly, if we curl our right hand fingers in this direction, so the thumb will point out in the positive Z. So we are assuming that MAX and MAY both are the counterclockwise moment reactions. So we have to find these 5 unknowns, and we have to find the tension in this cable. So now let me cut this rope. So if we cut this rope somewhere here, so we will have the tension in this rope, and the tension in this rope is going to act from C to B, and let's say this is that tension T. So we have to find this tension T, but before going to find this tension T, we have to represent this T as a Cartesian vector. So this T vector, as we know that this T vector, this will be equal to T magnitude times the unit vector from C to B, since the tension is acting from C to B. And this is T, and the unit vector from C to B is the position vector from C to B divided by the magnitude of that position vector from C to B. So first of all, we have to find the position vector from C to B. So as we have discussed several times, that while finding the position vector from C to B, we need to start moving from C along the X, Y, and Z, and we will try to reach that point B from C. So now from C, we need to travel 3 meters distance, this 3 meters distance in the negative X. So I will write 3 meters minus 3I, 3 meters in the negative I. So we will reach here. Then from here, we need to travel 1 meter and then 1 meter. So this 1 meter, once we reach here, then we need to travel 1 meter plus this 0.5 meters in the negative Y. So 1 plus 1 plus 0.5 is 1.5 in the negative Y. So that is in the negative J. So minus 1.5 in the negative J. So from here we will reach here, then we will reach here. So then from this point we need to travel 1 meters in the positive z, so plus 1k. And then the magnitude of this position vector that we have just determined, so the magnitude will be 3 square plus 1.5 square plus 1 square under the square root. So let's find this magnitude. This will be 3 square plus 1.5 square plus 1 square. This gives us 3.5. So this magnitude is approximately 3.5. So now we can say that this t Cartesian vector, this is equal to, now we have to divide each of these components by this magnitude. So we will have, and let's multiply this t with each component. So we will have minus 3 divided by 3.5 into ti, and we will have minus 1.5 divided by 3.5 t into j. Then we will have plus 1 divided by 3.5 into t, and then we will have k. So now we can simplify this 3 divided by 3.5. This gives us 6 divided by 7, right? If we convert this standard to decimal, from decimal to standard, this is 6 divided by 7. So we can say that this is minus 6 divided by 7 ti. Now 1.5 divided by 3.5, this gives us 3 divided by 7. So this is minus 3 divided by 7 t, this is j. And then 1 divided by 3.5, this gives us 2 divided by 7. So this is plus 2 divided by 7 t. You people can write these 3 divided by 3.5 as that decimal values. So 3 divided by 3.5 is 0.857. So we can write this ratio as 0.857. It doesn't matter. So I'm going to write this as fraction. So that's this t Cartesian vector is equal to this. So now we have, this is the tx component, this is ty component magnitude, and this is tz component. And the negative sign tells us that this t will have a component in the negative x, it will have a component in the negative y, and it will have a component in the positive z. So now let me represent those components. So we will have, since t is acting from c to b, so it will have one component in the negative x, it will have it will have one component in the negative x, it will have one component in the negative y, and it will have one component in the positive z. So let's represent all those components. So this is tx, the components of t along the negative x. This is ty, and then we will have tz. So this is tz. So now we know that this tx is minus 6 divided by 7t. This is plus this, the magnitude is 6 divided by 7. This magnitude is 6 divided by 70. Minus sign tells us the direction. Again, the ty magnitude is 3 divided by 7. So I will write this is 3 divided by 7t, and then tz is 2 divided by 7. So now we know all these components, and these components are given in terms of t. Similarly, to find this t, if I apply the summation of moment about point A, so the summation of moment about point A must be equals to 0, since this member which is supported is in equilibrium. And before going to apply the summation of moment about point A, we need to consider the weight of this cylinder. So the weight of this cylinder is going to act vertically downward. So let me represent that, and first let me cut this rope and let me remove this cylinder. So now we don't have this cylinder. We are going to consider the weight of that cylinder is tension in this rope. So this will be, so here we will have the weight, and that weight will be equal to 40 times 9.81, since the mass is 40 kg. So 40 multiplied by 9.81, this gives us 392.4. So this is 392.4. So the weight is, first let me write that weight as a Cartesian vector. So the weight is only acting in the negative z direction. So its I and j components are 0. So we can write that this is 0i plus 0j minus 392.4 k. So this is the Cartesian vector representation of that weight. Now we have to apply the summation of moment about point A, that must be equals to 0. And as we know that at A we have all these unknowns, so they are not going to produce the moment about point A. So only this t and this weight, they are going to produce the moment about that point A. So now we can apply the vector approach and we can apply the scalar approach to solve this problem, but for now I'm going to apply the scalar approach. So for now I'm going to apply the vector approach. So for vector approach, we have to find the moment of this t about point A using the cross product, and the moment of this weight about that point A using the cross product. So we can write that the moment of that t about that point A using the cross product will be r cross t, and then we have to define the moment arm for t. So the moment arm for t will be a position vector from A until that point C. Or we can define one another moment arm. That moment arm can be from A to B. Since the moment arm can be any vector, any position vector that will start from the point of rotation and that will end on any point on the line of action of that force for which we are going to find the moment. So either we can say that the position vector from A to C can be the moment arm, or we can say that the position vector from A to B can be the moment arm for finding the moment of this t. So for us, that will be easy to have the moment arm from A to B. So now let's say that the position vector from A to B can be considered as the moment arm for this t. And similarly, we have to add up, since this is the summation of moment about point A. So now for this weight, the moment arm can be a position vector from A to D. So we can write that the position vector from A to D and the cross product with that weight vector, and this will be equal to 0. So now we know how to find the cross product. So we have to write that as a matrix, and that will be I, J, and K. And then in the second row, we need to write the components of the position vector from A to B. So now again, we need to find the position vector from A to B. We need to move from A to reach that point B. So now the position vector from A is that we need to move 0.5 meters in the negative y, that is in the negative j. So I will write minus 0.5. So from A we will reach here, and then we need to travel 1 meters in the positive k, that is in the positive z. So plus 1, you will write plus 1, and there is no need to travel along the x-axis, so this will become 0. And here in the third row, we will write the components of this t. So we will write minus 6 divided by 7, that is the x component of t, the y component of t, and the j component of the k component of t. So this is the x, y, and the k component, that is 2 divided by 7t. Then we will write plus, and then again I, j, and k. Then we have to find the position vector from A to D. So from A, we need to travel 3 meters in the positive x, and then 1 meters in the negative y. And there is no need to travel in the z direction. So plus 3 in the positive x, then 1 meters in the negative j, and 0 meters in the k. And then the weight is 0, 0, and minus. So you write 0, 0, and minus 392.4, and this must be equals to 0. So then we need to add up, here we need to add up the moment about the x and the moment about the z, since we have these couple moments at A as well. So this is not equal to 0, we have to add up those moments as well. So this max, this is about the positive I, so I will write plus max in the positive I, let me write it like this, and then we have maz, that is maz in the positive k, this is equal to 0. So similarly, we have to add up both of those couple moments in this equation. So that is plus maxi plus mazk, this is equal to 0. So now we have to find these two determinants. So for I, we have to write it like this. We have to hide this and this. So the product of this minus the product of this. So we will write for I minus 0.5 into 2 divided by 7t minus 1 into minus 3 divided by 7t. Then for j, we need to hide this row and this column. So 0 minus this. and with j we always need to write minus sign, so minus j, and then for j 0 into this, so 0 minus this, so minus 1 into minus 6 divided by 7t. And similarly for k we need to hide this row and this column, so 0 and minus the product of that one, so this is plus k, and minus into minus 0.5 into minus 6 divided by 7t. So this is the determinant of this one. Then we have to find the determinant of this one. So for that again we have to write this is plus I, so plus I, and then for I we have to hide this row and this column, so minus 1 into this, so plus 392.4 minus 0, so for I we have to hide this and this, so this minus 0, so this is plus 392.4 I. Then for j, hide this row and this column, so this minus 0, so the product of these two, so minus j, then 3 into minus 392.4, and then for k we need to hide this row and this column, so 3 into 0 minus 0, so this is 0k, so plus 0k, and then we have to write plus maxi plus mazk, and this is equal to 0. So now we have to add up all the moments about the x-axis, that is the components along the I, the j components and the k components. So the I components, we have to add up all the I components, that is the moment about the x-axis. So first let me simplify this. This is minus 0.5 into 2 divided by 7, and then minus into minus 3 divided by 7. This gives us 2 divided by 7, so 2 divided by 7, this is 2 divided by 7, so plus 2 divided by 7i. Then we have this I term, this is plus 392.4 I, and then we have that max, the couple moment, the reaction about the x-axis, that is, so plus max, this is equal to 0. So this is our equation 1. Let me write this as equation 1. Then the summation of moment about the y-axis, that is the j components. So this j component is minus into minus plus 6 divided by 7. And here remember that here we have that t. Here we have that t, remember. So then we have this is plus 6 divided by 7 into minus, so minus 6 divided by 7t. Then we have this minus into 3 minus and minus plus, so plus 3 into 392.4, and this, and then there is no couple, there is no reaction moment about the j-axis, so this will be equal to 0. So this is our equation 2, and this equation 2 gives us, since in this equation only we have only this t as an unknown, so we will be able to find this t. So from this we can say that minus 6 divided by 7t is equal to minus, so this will be minus 3 into 392.4, and if we divide both sides by minus, so if we cross multiply this 6 divided by 7, so we will have 7 divided by 6 into 3 into 392.4. So we have 7 divided by 6 multiplied by 3 multiplied by 392.4. This gives us t equal to 1373 Newton approximately. So the tension in that cable from C to B is 1373 Newtons. Similarly, if we add up all the k components, all the moments about the k, so this term we will write minus into minus plus 0.5 into this, so the k components, that is 0.5 into minus 6 divided by 7t, and then we have this k component, this is maz, so plus maz, this is equal to 0. And from this we can say that the moment at A, that the reaction moment at A about the z-axis, this will be equal to plus 6 divided by 7 into 0.5 t. So we can write that 6 divided by 7 into 0.5, and now t magnitude is known, which is 1373. So 6 divided by 7, or we can say 6 multiplied by 0.5 multiplied by 1373 divided by 7. So this gives us 588. So the moment at A about the z-axis is 588.4 newtons, or we can say that this is approximately 588 newtons. So we got, out of those 5 unknowns, we got 2 unknowns. And here in this equation 1, if we look into this equation 1, we don't need to write this I, since this is the summation of I components. And now as we can see that we know this t. So if we know this t, we can substitute this t value and we will be able to find max. So let's find max from this equation 1. So from equation 1, we can write that max is equal to minus 2 divided by 7t, which is 1373 minus 392.4. So this is minus 2 into 1373 divided by 7 minus 392.4, and this gives us minus, so max is minus 784.69, or we can say that this is approximately minus 785. And remember, this is moment, this is not force, so this will be Newton meter, right? So this is Newton meter, and similarly this is Newton meter. And the negative sign tells us that we have assumed that the moment, the reaction moment at A about the x-axis in the counterclockwise direction, but it is acting in the clockwise direction, right? So if we curl our right hand fingers in the clockwise direction, so our thumb will point out in the negative x. So that is why we have that minus sign. So max is the moment reaction at A in the clockwise direction. So the minus sign tells us that it is in the opposite direction of the initial assumed direction. Similarly, to find ax, ay, and az, now we need to add up all the x, y, and z components. So let me copy this. So now if we add up all the forces along the x-axis, that will be equals to 0, since this member is in equilibrium. So again we have this ax, this is acting in the positive x, so I will write plus ax. Then tx is acting in the negative x, so we will write minus 6 divided by 7t, and this is equal to 0. There is no other force in along the x direction. So from this we can say that ax is equal to 6 divided by 7t, and t is 1373. So we will find it later. Similarly, if you find the summation of the forces along the y-axis, that must be equals to 0. So now along the y, we have that ay, this is in the positive y, so plus ay. Then we have this ty in the negative y, so you will write minus 6 divided by 7t, and there is no other force along the y direction, so this will be equal to 0. So from this we can say that ay is equal to 6 divided by 7 into t is 1373. Similarly, if we add up all the forces along the z direction, or all the components along the z direction, so we will have this az. So az, then we have tz. Tz is acting in the positive z, so we will write plus tz, and tz is 2 divided by 7t, so plus 2 divided by 7, t is 1373, and then we have this weight in the negative z, so we will write minus, and the weight is 392.4. This is equal to 0. So from this we can say that az is equal to minus 2 divided by 7, 1373, and plus 392.4. So let's find ax first. So ax is 6 multiplied by 1373 divided by 7. So this gives us AX equals to 1177 Newton approximately. TY is 3 divided by 7. This is not 6 divided by 7, right? This is 3 divided by 7. This is 3 divided by 7. So now we have 3 divided by 7 into 1373. This gives us 588. So AY is approximately 588 newtons, and similarly using this we can find AZ. So this is minus 2 multiplied by 1373 divided by 7 plus 392.4. So this gives us 0.11. So approximately this is equal to 0. So we can say that AZ is very small, and this is equal to approximately 0 newtons. So this is the solution of this particular problem. I hope it will help you in your learning. Do like this video and let me know in the comments if it helps in your learning. For more, subscribe Engineers Academy.